Kotala from Sun, and he's going to tell us about multi-threading programming and some problems with it, I think.
Yeah. there are a lot of problems. I work for Sun in a Prague office. I'm a member of Solaris Revenue Product Engineering Group, and my responsibility now is fixing bug in security technologies like Sun SSH and PKCS 11. I'm also responsible for integration of PostgreSQL into the Solaris. It's my second responsibility now. There is the topic multi-threaded about multi-threaded applications were very big, and I will focus only on few parts which I met during my career and which I usually fixed. I will talk about process life and signals, how signals are handling in multi-threaded application. What at-fork handler is, and how to protect memory access, and how to use sessions in multi-threaded application. Why I prepared this presentation? I have in my first job, I developed application. I spent 1 month in developing application and 3 months where I hunting bugs because. I didn't understand the technology, and I didn't know that how Microsoft Internet server works, and I completely badly designed the application. It takes 4 months completely to finish the work. Customer was really unhappy with this situation, of course, because he put this my code into the productions, and it falls 2 per day. In my former company, again, I spent 3 weeks to rewrite the signal handling. It was not my bug, but I spent 3 weeks to rewrite signal handling in applications. It was very funny because it worked correctly, or mostly correctly, on 264 platform. When we ported this application to the Linux, it hangs each 1 hour, because the signal handling on Linux was different than on 264, and it's the timing of something in kernel was different, and it hangs in each 1 hour. I needed to spend a lot of time to reading the specification, POSIX standard, made some experiments how it really works, and fix it. And now I spent half a year fixing the bug in PKCS 11 library related to multi-threaded environment. You can see the few of them. It's not complete list. If you look on the libc, you can find a lot of bugs. If you want to look on the fork problem, you can see a lot of bugs. Now I will start with process life. Usually when you write the program, you start with the main functions, but it's not a real beginning of the code, because linker or compiler adds some prologue before the main functions and some epilogue at the end of your program to set up some libraries and clean up after you leave the main functions. It is important to know, because in a single-threaded application it doesn't matter, because you have one thread, you return from main functions, and exit syscall is performed. If you have a multi-threaded application and you still have more threads living during you leaving the main functions, the epilogue starts to clean up the libraries and clean up the memory and so on, and other threads wants to access this piece of code, a piece of memory or data structure, but it's already released you can see some crash dumps or core dumps or something like that. It's very important if you write the application, multi-threaded application, to stop all threads before you leaving the application. I seen exit call in one application. I seen exit call everywhere in the. Okay, it fails. Okay, write a message and exit. Nobody cares about what's going on in another threads, for example. Yeah. It's also very important if you write the library. Just library. If library needs to clean up some memory structures, or if you use PKCS11 library, it's for example connected to some hardware, secure hardware, and you need to clean up some keys or something. You need to do something with the hardware also when you're leaving. Just it's very important to know how it works. Okay, I will show you the how code looks like. If you look, it's very important to sometimes look on the code in Pulsolaris. Just is it okay? This is assembler. It's for x86, and this is part which start that you can see the init sections which initialize the libraries and perform some basic configuration, and there is calling the main functions. You can see it, and when you leave the main functions, when you call a return, there is the call exit. Or you can see that there is the syscall finally. If you redefine exit, this is some protections to really exit the application if you redefine exit functions. And when you exiting here, exit functions perform all at exit handlers. You can register at exit handlers in your application, and when you call exit, these at exit handlers are performed. Usually, this at exit handlers are also used that library register here the finalized sections of the library here. Just for example, PKCS11, if you library, when you exiting, that it calls the cleanup. But other threads, if other threads already still works on some encryptions algorithm, and you start to clean up data and untouched hardware or some crypto hardware or something like that. You can get very nice messages or some crash dumps for analysis. You can usually the init sections is when process started, it's single threaded. And it started with init sections. The init section is usually in the single threaded environment, runs in the single threaded environment. But if you open some libraries by the dynamic load open functions, DL open functions, you already can have more thread activated. It's you need to know that it's not every. You need to know this that sometimes it's not only single thread process when any section is run. And this is also important. And as I mentioned, don't call exit functions when more threads are still run. What I recommend is to have one main thread which control all worker threads and which is responsible to collect all threads and kill or stops all threads before the application is leaving. And which also clean up the resources. Okay. Signals. Yeah, signals is very nice part of multi-threaded applications. A signal is asynchronous event. Somebody can send kill hub or kill term or something like that to the application. In the single-threaded application, the process get a signal, and if signal is not blocked, the signal handler is process it. Just start and do some job and return back to the application. There is few there is a big limitation of what you can do in signal handler. You cannot. For example, a very nice signal handler has a GNOME. It's open the window and print. Okay, something crash. It's a very bad idea to do that in signal handler, but you can see usually on Solaris that it hangs in some memory allocation or somewhere because it's not signal safe to do that. But if you have a multi-threaded application, the situation is more complex, more complicated, because signals are for communication mostly between processes, and you need to know, or usually you would like to process signal. You want to have a control on when and where you want to process the signal and signal handler. The POSIX standard specify or says that there is no there is when signals arrives to the application, multi-threaded application, any of thread can handle this signal. Of course, if it's not blocked for the thread, just you don't know which thread will process the signal. But usually you want you don't want to interrupt the worker process or worker thread. Just one method how to do that is to block all threads, block signals in worker threads, and keep only one thread for processing this signal, unblock the signal. You need to first because the thread inherits signal mask from the parents threads. It's very important to block all signals before you created the new threads. And when you create the new threads, you should release the setup back to the signal mask. Because if you don't do that in this way, there is the small race condition between creation process and blocking creation thread and blocking the signals in the thread. It's better to do it this way. Another approach is to dedicate it one special thread which is responsible for handling signals. As I already mentioned, the signal handlers has limitations. You cannot use this bunch of functions here. You cannot use mutexes or something like that. Signal handlers in multi-threaded applications runs in parallel with other threads. If you want to access some memory in signal handler, you need to somehow protect this memory if you want to also touch it from another threads. Yeah. And you cannot use mutex because if some thread logs mutex and you call the signal handler, it's typical deadlock. Yeah, just don't use mutexes. I also seen the mutexes in the signal handlers. Don't do that. Yeah.
Can I have a fast question? Is it safe in signal handler to make some condition variable because that would be natural?
It's not safe. It's not safe. It's because condition variable also uses internally mutexes. Just you cannot use it. It's not. It's why I recommended the second approach is to dedicate it to one thread, which will be responsible only for signal handling. This thread yeah, there's the example how it looks like. It's also some examples in my paper. This is a simple signal thread. Just use these sig_wait functions. You have to block all signals and just let sig_wait functions which wait until some signals arrives. There is still some signal set. Okay, it's not defined here, but it contains the signal mask which you want to process, and you can do there the reconfiguration or stopping all other threads, what we want to do, but without any limitation because this is not signal handler. It's standard function, standard thread. Yeah, you can do it safely, and you can use mutexes and so on.
Would you recommend one thread per signal or one thread for all signals?
Probably it depends on what you want. I think the one thread per all signals. Because you usually need to handle the hub signal for reconfiguration and 3 signals, which is okay, I can quit and so on for stopping application or receiving application, and you can do that in one signal handler, one thread. Yeah, but somebody can have more complicated situation. For example, user 1 and user 2 signal can do some biggest operation, and maybe it's better to split it for two or 3 threads. I don't know. It depends on application, but mostly I think it's one thread. It's good enough. Okay. Signal. Okay, and there is my preferred topic, the at-fork handlers. It's all of bugs which I put it on the first slide. It were mostly about at-fork handlers. Do you know what fork does? Yeah. Do you know what it does in multi-threaded application? Yeah. It's very interesting because many people don't know it. I personally didn't know it also before first escalation, which I need to solve, because personally, who needs to fork in multi-threaded application? Yeah, it's not a common thing. Yeah, but there is 2 reasons for that. First reason for forking multi-thread application is exec. You need to fork an exec. It's mostly okay. There's usually not so problem. If you do a fork and immediately exec, it's not problem. But if you have some code between fork and exec, you can have, and usually you have a problem. And second reason for it is Java. I don't know why Java do the fork, but Java Crypto framework uses PKCS11 library on Solaris directly for speed up crypto operation. Because the crypto framework on Solaris uses hardware and crypto hardware and so on. And I don't know how it works in Java, but it's somehow calls the C library, and sometimes it's fork. I don't know why, but it's very common. We have a lot of escalation about it, and it's not for exec because it's the Java's continue work with this. Just fork the application and continue. There is a lot of problems with fork and multithread. Or there is one big which we can split in many small problems. The problem is that fork only fork the calling thread. Just after fork, you have one thread, and other threads are clean up. Just only if you want to fork all threads, you need to call fork all function, but it's not standardized. It's Solaris specific functions. But fork call creates children process only with one thread. Okay, one thread is okay, better than 0. But all other state of application still remain. The lock are still locked. Condition variables still in their previous state. And if some other threads lock some variables, and after fork it's locked some mutex. After fork, the thread doesn't exist, but the lock is still locked. You cannot continue usually because it's typical deadlock. I will show you a few demos of this, and it's the reason why @fork handlers exist in the POSIX standard. And probably if you look in the, it's interesting bugs, for example, in multi-threaded empty memory allocation, which is primarily dedicated for multi-threaded application, for speed up malloc and so on. It also doesn't work correctly with fork on Solaris 10. In Nevada it's already fixed, but on Solaris 10 it's not fixed, I think. Maybe now it's 1 month ago it was not fixed yet. @fork handler is a method how to do that, how to solve this problem. You set up the functions which is called before the fork, and you set up two functions, one for parent, one for child, which is called after the fork syscall. Just you have to acquire all logs or condition variables on some this problematic piece of data structures, and after the fork you need to release it again. In some special cases, I will show you the special case. You need to reinitialize the log because I will show the big why. And very important thing is that @fork handlers are processed in parallel with another thread. Okay.
That's my question. Which thread context are these called within? So it's the fork syscall or the fork library call that I do that walks the list of @fork handlers. So it's
fork. No, syscall doesn't do that. If you call fork libc.
Yes, I know. Yeah, that's what I mean.
Yeah, the fork functions prepare everything for fork, including calling the @fork handlers.
Ah, okay.
Yeah, I will show you why it's in a special case in a PKC11 why I need to reinitialize global mutex, because it's not possible to lock it and unlock it.
So, but if things are going bad, then the fork library call might take very long. Okay.
Because each library has to have the fork handlers.
Yeah.
Because typical each library has some mutexes or so on.
And they're not called in parallel; they are called sequentially, one after the other.
Fork handlers, yeah. There is it's I'm not sure now. What's the order? It's how we register this. It's called in the order and opposite order of, after the fork. But I don't know which order is selected now. But it's if you read the POSIX at fork handler in the POSIX standard, there is the explanation how it's. But it's very important. The order is very important. I will show you why. But at fork handlers are called synchronously, seriously, but other threads still works because it's libc in the libc. You need to keep the lock order in the at fork handler to protect the locks. It's very important.